In this lesson, we're going to be looking at inverse functions, but really we're going to be looking at inverse functions from the perspective of graphing inverse functions. And so what we're going to do is we're going to graph a function and its inverse, and we're going to kind of compare these things and see what relationship we come up with between the graph of the original function and the inverse, all right? For example, when I look at this first one, here, to find the inverse, I just reverse each of these ordered pairs. I switch the x and the y, so it's going to be 3, 2. The next one's going to be a 4, negative 1. A 3, 0, and a 5, negative 4. All right, so this is my inverse, and now I'm going to graph each of these, and you notice the original function I have in blue, so I'm going to graph that in blue. The inverse I'm going to graph in purple, and so I just plot each of these ordered pairs. So I've got 2, 3, I've got negative 1, 4, 3, 0, 3, negative 4, 5. Right here. Okay, so this is the original function. I've got it graphed here in blue, and now I'm going to graph the inverse in purple. So I just plot each of these ordered pairs again. So that's 3, 2, 4, negative 1, 3, 0, and 5, negative 4. All right, and so as I look at this thing, I should recognize some kind of pattern here as I compare the purple dots and the blue dots. I should recognize that these things are symmetrical. And they're not symmetrical in the sense that we're typically used to things being symmetrical. Like when we looked at parabolas, those are symmetrical from left to right. They're cut in half right at the vertex. And there's certain things that are symmetrical up and down. This one is symmetrical, but it's kind of symmetrical on a little bit of a diagonal axis. And so if I draw the line of symmetry here, if I draw this diagonal line, it should make it easier to see. So if I draw this diagonal line now, you should be able to see that the blue dots and the purple dots are clearly a mirror image of one another over this green dotted line. All right. So these are reflected over this line, and the interesting part is this is the line y equals x. And the reason that's so interesting is because when you think about what the inverse is when we switch the x and the y. So essentially, when we do the inverse, when I switch the x for the y, I'm saying that y is now equal to x, and I'm saying that x is now equal to y, and now I'm reflecting over the line y equals x, or x equals y. All right, so it's interesting from that perspective. I'm reflecting over that line where x and y are truly equal to one another. The other interesting thing here is we kind of think of it from the perspective of the composition test. The composition test, I plug one function into the other function, and it kind of like averages out these points. If I average out these 2 points, it lands me right here in the middle on this y equals x line. Same thing here. If I average out these 2 points, it lands me right here in the middle. If I average out these 2 points, it lands me right in the middle. If I average out these 2 points, it lands me right in the middle, right on y equals x, which is why when we do the composition test and we kind of balance these things out, we plug one into the other, they cancel out, and I'm left essentially sitting on this line, and that's why the composition and its inverse equals an x. It's like I'm averaging out to this line. So there's a couple neat things here. And really the big thing that we're going to use this for is to graph functions that we're not quite as familiar with. Because keep in mind, if I had just graphed the blue functions, or the blue dots here, I could reflect that function, knowing that it's reflected over the line y equals x. I could have come up with all the purple dots without actually writing the inverse of this thing. And that's what we're going to do. We're going to use functions that are a little bit more familiar to us, and then reflect them to come up with functions that are a little bit unfamiliar to us, and to explore things like square roots. Okay? So if I look at the next one, I'm going to start off, I'm just going to graph the original function, so let me put my line of symmetry here. I know that the inverse is going to be reflected over this line, so I'm always going to start with this line being on here. And so now what I'm going to do is I'm going to plot the original function. I'm going to plot g of x in blue. It's got a y-intercept of 3 and a slope of 1, so I have to go up 1 over 1, up 1 over 1, or down 1, back 1. So I go ahead and I plot this line, and now what I want to do is I want to reflect this. So if I'm reflecting diagonally, I would like essentially count to the line and then count over in the opposite direction, so I would have a point here. All right, and so I can reflect that point. And when you look at the ordered pairs here as I reflect that point, if I were to reflect another one, let me draw another one real quickly. Like if I were to reflect this point, it would end up right here. Sorry. Right here. There we go. So if I reflect that point, so now let's take a look at these points in a little bit more detail. If I look at these points in a little bit more detail, think about the ordered pairs here. Like the ordered pair of this first point was 0, 3. And notice its reflection point is 3, 0. It's the exact inverse point where I switch the x and the y. Here, the ordered pair of this point right here, which is the next one that I reflected, was negative 2, 1. And if you look at the reflection, it's 1, negative 2. All right, so there's a couple ways to think about reflecting over this. You can kind of count diagonally, which is kind of tough to do. It's easier just to look at each individual ordered pair, and if you really break this down into ordered pairs, which is the most basic thing we understand about inverse functions, is switching the ordered pairs. If I just take each ordered pair that I can see and switch it, I'll come up with a whole list of ordered pairs here that's going to allow me to graph this function. And so as I graph the inverse here, there it is. There's the reflection of that blue line, okay? And of course, in this one, I could have found that algebraically. If I switch the x and the y, I rewrite this as x equals y plus 3. And now solve this for x by subtracting the 3 from each side. I'm going to find out that the inverse is y equals x minus 3. So when I look at this, the inverse here, let me write it in purple since I have it graphed in purple, is x minus 3. And when I look at that graph in purple, it's got a y-intercept of negative 3 and it's got a slope of 1. And notice it's reflected over that line y equals x. Okay? The other interesting thing here is that everything that was true about x for one function is now true about y. Like, if I look at the blue function, it had a y-intercept of 3, and this one has an x-intercept of 3. The original function had an x-intercept of negative 3, and this one has a y-intercept of negative 3. Okay? So all the properties of x from the first function are now properties of y, and all the properties of y are now properties of x, which is kind of neat, and it's going to help us do a little bit more with these graphs. Okay? If I look at something like this guy, this is kind of a unique case. If I were to draw that line of symmetry here, so here's my axis of symmetry, it's that line y equals x. But now the function in blue, I'm graphing y equals x, so I'm going to draw that right on top of the axis of symmetry. And now if I were to reflect those points, again, reflecting them, I can try to count diagonally, which is weird to do here. Think about switching each of these ordered pairs. Like here, I've got the ordered pair 0, 0. If I switch that, I get the ordered pair 0, 0. So I would plot a point right here. For the next one here, I've got the point 1, 1. If I switch that, I still end up with 1, 1. So I get a point here. So as I start to graph this thing, I find out that the inverse is graphed right on top of this thing. And this is a very unique case. This is a special case where the inverse and the original function are the same thing. So this time the function is its own inverse. And we can see that algebraically as well. If I were to switch the x and the y instead of y equals x, now I'm going to have x equals y. So I switch the x and the y. If I rearrange this and solve, quote unquote, for y, I'm going to have y equals x. So the inverse of this one equals x. And that makes sense because when you look at all the ordered pairs on this one, every ordered pair that's on this line, the x and the y value are the same, so switching them doesn't change anything. I've got ordered pairs like negative 1, negative 1, negative 2, negative 2, 5, 5, 6, 6, okay, 8, 8. All right, so switching them doesn't change anything. And the other thing that should show us here is that if we have functions that intersect this mirror, the inverse is going to intersect the mirror at the same spot. If we hit the line y equals x with our function, the inverse is going to touch that line at the same spot. If we pass through at that point, the inverse is going to pass through that point as well, okay, because they have to have that point in common, because when you switch the x and the y's, it doesn't change. All right, and when we look at an example where it does that, if I look at this next one, if I look at something like this guy, again, I'm going to start off with this line y equals x. This is my mirror, and now I'm gonna plot the original function. Again, I'm gonna do it in blue. It's got a y-intercept of negative 3, and it's got a slope of 2, so that's up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and I just draw my line. And now if I want to reflect this thing, again, start breaking it down in terms of ordered pairs. Down here I have the ordered pair 0, negative 3, so I'm going to have negative 3, 0. On the original function, I have 1, negative 1, so I'm going to do negative 1, 1. Okay, and so I can start to reflect each of these points, and as I do that, I come up with a line that kind of looks like this. And what's interesting about this, sorry, I got a little off as I drew my line here. Let me try that again. what's interesting is that these are still reflections of one another. It might be hard to see, but if I just looked at like these bottom two pieces, those are obviously a mirror image of one another. And then if I change that around and just looked at the top piece of this thing, those are clearly mirror images of one another. And so what happens is as I intersect that mirror, I cross over to the other side. The inverse has to do the same to keep these things reflecting one another. But again, those properties of x and y are still there. On the first function here, the x-intercept was -3, and that's the y-intercept on the second function. On the first function, the y-intercept was 1.5. That's the x-intercept on the other functions, okay? So all the properties of x and y have changed. And if I find this algebraically, just to make sure this matches, if I switch the x and the y, so x equals the 2y minus 3, I'm going to go ahead and add that 3 to each side. So I'm going to end up with x plus 3 equals 2y, and then divide by the 2. When I do that, I'm going to find out that the inverse here is a 1/2 x plus 3/2. And when we look at that, my purple line has a y-intercept of 3/2, and it's got a slope of 1/2, okay? So now let's look at something like this, all right? If I look at something like this, I'm not familiar with the graph of the inverse here, so I'm actually going to find the inverse first because I'm not familiar with it anyway. So if I switch the x and the y, I do x equals y squared plus 2. When I do this, I'm going to go ahead and solve this thing. I'm going to subtract the 2 from each side, and then I'm going to take the square root of each side. When I take the square root of each side, I have to remember that when I take the square root of each side, I have to do plus or minus here, so it's y equals plus or minus the square root of x minus 2. And so this is my inverse here. The problem is I don't really know what that inverse is supposed to look like. So let's think of it in terms of the graph of the original function. Since I know what the graph of the original function is supposed to look like, because it's an x squared, I know it's going to be a parabola. And that parabola is actually in vertex form, so I can see that the vertex is 0, 2. The a value here is a 1, so it opens up and it has the standard shape, so over 1 up 1, over 2 up 4. So it has my standard width of a parabola. And now I can graph this parabola. And then what happens is I can reflect this. So I take each ordered pair. I have that ordered pair 0, 2. That becomes a 2, 0. I have the ordered pair 1, 3 becomes a 3, 1. I have -1, 3, so 3, -1. I have 2, 6, so 6, 2. And then I also have -2, 6, so that's 6, -2. And so the graph that I come up with here is kind of this sideways looking parabola. So what that tells me then, if I'm looking at inverses, and inverses are always reflected over this line, well, an x squared function is always a vertical parabola, a parabola that opens up or down, which means a square root function, because anytime I find the inverse, anytime I undo a square, I'm going to use a square root. So if a square function is always a parabola that opens up and down, a square root function is always going to be a parabola that opens left and right. And then when we look at the plus or minus on this thing, this is where it becomes really interesting. If I were to get rid of that plus sign, if I were to scribble that out and just have the minus, well, what would happen is I would only have the negative half of this parabola. I would only have this piece down here, all right? And if I were to do the opposite of that, if I were to scribble out the negative sign and only have the positive version of this square root, well, that means that I would only have the top half of this parabola. I would only have this guy up top. All right? So what happens when I have a square root, I'm going to get some form of a sideways parabola. The plus or minus gives me a full sideways parabola. Without that, it's going to either give me the top half or the bottom half. Okay? And so when I look at this next example is just the positive version of that square root function. So if I just have the positive version of that square root function, I'm only going to graph the top of it, which means I'm just going to have this piece right here. And now what I want to do is I want to find out what the reflection of that is going to be for my inverse. And so what happens here is I'm going to go ahead and reflect this thing. And as I start to reverse those ordered pairs and reflect each of these points, I get a point here, here, and here. So my graph, according to reflecting this thing, just looks like this. So I end up with half of a vertical parabola. Okay? And so let's see how that translates into actually finding the inverse algebraically. So to find this inverse algebraically, what I'm going to do is I'm just going to take this guy down here and let me switch the x and the y. So this was y equals the square root of x minus 2, so I'm going to do x equals the square root of y minus 2. And now when I solve this thing, I go ahead and I square each side. So that's going to give me an x squared equals a y minus 2. And now I add the 2 to each side. And when I do that, I find out that my inverse is going to be an x squared plus 2. And when you think about the graph of x squared plus 2, the graph of x squared plus 2, if I do this in another color, let's see what else I have here. Let me just do this one in black. I've got a vertex right here, but then this graph of that inverse of x squared plus 2 is this entire vertical parabola. And so the issue with that is I know because of reflection that I should only have half of a vertical parabola. And so what this leads me to believe is that algebraically, what I have to do to compensate for this is basically I have to restrict this thing. See, if I were to ask for the inverse of this thing, the inverse is not x squared plus 2, the inverse is x squared plus 2 when I only use the x values that are greater than or equal to 0. So we have to put that restriction on here in order for our inverse to match what the original function was actually telling us to do. Okay, so because I only have half of a sideways parabola for my original function, the inverse has to be half of a vertical parabola, and that's it. Okay.